Today we're going to dive in and write our first compiler optimization. We're going to start with a few simple optimizations around the theme of dead code elimination. But before we do that, I want to give some framing for different kinds of optimizations we'll study in 6120. The difference is between how we deal with control flow in the program. So you'll remember from last time that we started drawing control flow graphs, that is, breaking up programs from just sequences of instructions to these graphs indicating basic blocks and how control transfers between the basic blocks. So here's a sample CFG. At a very high level, in this class, we're going to categorize optimizations into three different categories. Local optimizations work within a single basic block. That means they don't have to deal with control flow. They just have to deal with the ordering of instructions in a sort of linear scan. Global optimizations work on an entire function. This means they have to deal with control flow. And as we will demonstrate in this video and the next one, dealing with control flow makes optimizations, typically speaking, much more complicated. Finally, there's a third category of optimizations we'll get to later in this semester, which has to deal with multiple functions. And those things are called interprocedural optimizations. Local and global optimizations can also be called intraprocedural, especially if you spell it correctly. But the words interprocedural and intraprocedural sound so incredibly similar to each other that it's more useful to say local and global when you're referring to things that work within the scope of a single function. But one thing to remember is that when you say global, you might think that, well, global, that means the entire program. That's not what people mean. By global optimizations, people mean global with respect to a single function. Interprocedural optimizations are a even fancier level that goes beyond global and looks at calls from one function to another. So if this basic block, for example, had a call to this function, we'd have to sort of reason about those calls. When we're doing global optimization, we don't even reason about calls. We're going to start out by thinking locally, that is, within a single basic block. We will also see some optimizations that apply globally to the entire function in a kind of trivial way first. And then later, in a few more lessons, we're going to see more sophisticated ways to reason globally, that is, to reason about control flow. And I hope that one of the things you'll take away from this video is understanding what the fundamental shift in thinking is that has to happen when you transition from thinking within a single basic block to thinking about an entire CFG. Let's start out by looking at a Brill program that it's possible to optimize. We're going to start out by thinking about dead code elimination, which is a simple kind of optimization that removes code that can't possibly have an effect on the output, thereby making the program faster. I hope you're getting more familiar with Brill programs and this instruction-based syntax and the semantics of the various instructions. So I hope you're able to understand this simple program that just does a couple of adds of constants. And my question to you is, what should we do to this program in order to make it faster? Where is the optimization opportunity? Of course, it's not too hard to see. There is this one instruction here, this assignment to the variable c, that is never used anywhere in the program. And so it's possible to delete this instruction and to get an equivalent program that runs faster. That is, it uses one less instruction when executing, but does exactly the same thing. So the next question I have for you is, what is the general principle, that is, can you phrase it in a sentence, for what opportunities exist, like this one, for optimizing Brill programs? That is, if we were to implement an optimization, what would we be looking for? Try to phrase that in a sentence. Try actually writing it down. Here's how I would phrase it. We can delete any instruction that assigns to a variable that is never used as an argument anywhere in the function, as long as that instruction has no side effects. By side effects, I just mean that we shouldn't eliminate instructions that don't seem to assign to a variable, and yet they have an effect on the outside world. For example, Brill has a print instruction. You can say like print C, for example, and it shouldn't be penalized for the fact that it doesn't assign to a variable, and therefore it seems to be dead because it doesn't produce any values used elsewhere. The criterion that we can use to do some dead code elimination is just to eliminate every instruction that has this pure semantics that all it does is assign to a variable, and that variable is never used by any instruction everywhere in the entire program. Therefore, this is a global property. We've come up with the framework, at least, for a global optimization that needs to look at the entire function. We happen to be looking at a function here that only has one basic block, but this is a global property. It's not possible to implement by looking at a single basic block. It's possible that you don't use C in this basic block, but in a larger function, for example, then you jump to another basic block that does use C. Therefore, this is a global property. To turn this into a real optimization, I would like you to now try writing the pseudocode for an optimization that carries out these instructions. That is, that analyzes a program and deletes every instruction that is dead by this definition of assigned to a variable that is never used anywhere and also not having any side effects within the instruction. Go for it. Here's my pseudocode. It works in a kind of two-pass style. There are two loops. The first loop loops over all the instructions and accumulates a big set of all the variables that are ever used anywhere in the function. The second loop goes over all the instructions a second time and looks for instructions that have a destination, and that destination is not in the used set, and it deletes those instructions. This relies on a simple property about Brill, which is that the operations that are built into the standard Brill don't have side effects if they assign to a value. That is, they can do one of two things. Either they are effect operations that don't produce results, or they're value operations that don't have side effects and they only produce results. This is true of the basic Brill instructions. If we're to make more complicated instructions, we'd have to think more carefully about what the side effects of instructions are. But for example, the print statement doesn't have a destination field. It doesn't assign to anything. So this instruction won't have, the print instructions won't have a destination, and therefore we will never delete those instructions. So that's a really simple implementation of our very first optimization. Great work. I want to now show you a second program that we're going to want to worry about how to optimize. As a first step for this program, I want you to try, in your mind, running your pseudocode for dead code elimination on this program. Do that now and figure out which instructions it would delete. My implementation, at least, would delete only this instruction. That is, this is the only instruction that's unused. And the tricky thing about this is that by thinking with your human brain, you can also realize that this instruction is also needless because it feeds into an instruction that is never used anywhere. But it doesn't meet the criterion that I set out in my pseudocode. That is, this instruction, the one that assigns to C, it doesn't have the property that it is never used in any instruction ever. So it's sort of disappointing. We know there is more opportunity to optimize here than we are giving credit for. That is, we're unable to do an optimization we'd like to do. So now I would like you to think for a second about how you can rectify this, how you can take the pseudocode that we wrote for simple dead code elimination and make it slightly more powerful to capture this case as well as the previous case. There are several ways to do it, but there's one way that's particularly easy, which is just to do the same thing multiple times. That is to run the algorithm repeatedly until it converges. And by that I just mean in pseudocode, just stick the code we had above in a while loop and run it while anything has changed about the program. This just means that we will keep running the dead code elimination, and the first trip through the while loop, we will delete this instruction, and then we'll run again, and then we'll notice that this instruction is no longer used by any instruction globally in the entire program, and we'll delete that too. This may not be the most efficient way to do this, but it is definitely the easiest. That is, all we need to do is take a single pass optimization that we've reasoned about to be at least correct and iterate it to convergence. That is, run it until nothing changes anymore. Iterating things to convergence is going to be a cornerstone of lots of the optimizations we see in this class. I want to show you one third and final program that's going to stretch our dead code elimination abilities. Here's the program. I want you to think for a second, again, about what our algorithm so far, including iterating to convergence, will do to this program, and what opportunities that leaves on the table. If you said nothing, you're correct. The previous algorithm would do absolutely nothing to this thing, even though the opportunity for optimizing it is fairly clear. That is, this assignment to the variable a has no effect on the output of the program. The only one that matters is the second constant in the program. Clearly, there's an opportunity here to do stronger dead code elimination if we can find variables that are assigned to and then assigned to again before they're used again. I'm going to caution you, however, that this property is a little bit more subtle to implement than the previous one that had to do with just looking global at the entire function and looking for uses of the variable. And the reason for that is because it has to do with the ordering of things. That is, the previous one really didn't care about the order of instructions. It was just saying, if you ever assign it to a variable in the entire function rather, that variable is never ever used by any other instruction, then we can be guaranteed that it's safe to delete. That's not true. That sort of like big bag of instructions model is not going to work for this type of optimization. In particular, we're going to have to think carefully about what happens globally in programs that have control flow. Let's imagine a slightly different function that has an assignment to A, and then it has another assignment to A, but in between there is a jump to a label where we print A. Of course, this code that doesn't ever get executed under this jump, that's eliminatable by a different kind of dead code elimination. But you can make this even more interesting by eliminating that possibility by changing this jump if you want to instead be a branch on some dynamic condition, say like we branch on some input we don't even get to see to either L or to K. So we can't possibly know at compile time which of the two assignments to A, this one or this one, will actually be the one that flows to the print. That is the one that actually matters for printing stuff. In this case, I think it's fairly clear that there actually isn't really an opportunity for redundancy elimination. There may be other things we can do to this program to simplify it so we're not like assigning to A and then reassigning to it. There may be other things we can do, but it's not going to be as simple. That is, like, there's not going to be a dead code elimination opportunity here. It's as simple as just deleting an instruction. And if you wrote an optimization based on the example on the left that naively assumed that all we had to do was scan through and look for assignments to the same variable that happened twice in a row, then we might think that we can eliminate this instruction. And that's clearly not true. Instead, in order to get this right, we would have to reason globally about the control flow of the program. That is, we would have to think in terms of the control flow graph that says that we have an A assignment here and an A assignment here, and then finally a use of A in the final block. Instead of doing that, what we're going to do at this juncture is just reason locally. That is, by restricting the reasoning to think only about these redundant instructions within a single basic block, we can avoid the entire problem of reasoning about control flow, which creates a much different kind of problem we'll solve in a future video. But for now, there's enough to be done just thinking about programs like the one on the left. That is, where there's an opportunity for reducing redundancy within a single basic block. That is, that there's a local optimization to be done that doesn't have to reason about control flow. And that property, just to state it clearly, is that we can delete instructions that assign to variables that are then reassigned later within the same basic block, just sort of later in the sequence of the instructions within the block, before they are ever used in any other instruction. So now I would like you to write down some pseudocode for how to implement that local optimization that reduces dead stores to variables within the context of a single basic block, a local dead code elimination based on overwritten variables. This will be a little bit more complicated than the previous one, so take your time and write some pseudocode now. Okay, here's my idea for how to do this algorithm. I'm interested to hear, if you want to post on Zulip, what you did differently, because I think there's a lot of different ways to do this. But here's my idea. We're going to start, of course, by doing a for loop over the instructions, but this time, instead of doing instructions in a program, we'll now loop just over the instructions in a block. My idea is to keep track of those variables at every point in the block. That is, after every instruction, we're going to keep track of those variables that have been defined but not used. That is, variables that have been assigned to, but they haven't actually been consumed yet. So these are the candidates for deletion. And if we ever see another assignment to that variable before we get to the end of the block, then we know that the previous assignment is worth deleting. So this means that we will preserve variables that are assigned to but never used once we get to the end of the block, because we might be jumping somewhere else that's going to use those variables. And we're not going to worry about global optimization at all. But we can say that if we ever hit one of those candidates for deletion, that it's defined but not used, and we hit another definition, then we know that there's a deletion opportunity. So here's my idea. We're going to have a mapping called lastDef that keeps track of those variables that are defined but not used yet. And this is going to be a mapping from variables to instructions. So this is going to keep track of the last definition, the most recent definition, but only of variables that haven't been used yet. So in the instruction, we're going to do this in two phases. In the loop, rather, we're going to do this in two phases. We'll first check for uses, and then check for definitions. It has to go in this order because instructions can be both users and definers. That is, if you say like x equals x plus 1, for example, you're using x and then defining x again. And we don't want to consider x dead just because we're assigning to x, because we're also reading the previous value of x. In any case, we need to check for uses first. So the way this will work is that we'll look at whether the instruction has any arguments. And if so, we will take those things out of our lastDefs. Remember that this lastDef thing, I'll do minus equal to say we'll take out all those variables that are now being used. LastDef is meant to keep track of all the variables that have been defined but not used yet. And we're encountering a use of the variable for everything in instr.args. So we're going to take it out of this candidate for deletion. Okay. The next thing we need to do is to check for definitions. And there's two things we need to do definitions. We need to put things into the candidates for deletion, and we need to mark things, and we need to actually delete some instructions if we notice an opportunity for redundancy. So the way that works in Brill is that instructions have a dest field, which is the variable they assigned to. What we're going to need to do is check whether we have any candidates for deletion, that is things that have been assigned to but not used that we're now reassigning to. So we can say, if this destination, that is the variable that we're defining now, is in lastDef, then we know it's time to delete. And what we'll delete is the instruction there. So just to illustrate what's going on here, in this case, we have something that looks like x equals 5, for example. And this is the instruction we're currently processing. And then the last definition for x is something like x equals 2, and that's the thing that happened earlier in the basic block, and that's the thing that we know we can delete. Regardless of whether we delete instructions, however, we also need to update our bookkeeping map. That is, we need to update lastDef. So we're also going to have to say that now, after doing that, that is like either deleting the instruction or not, we now know what the last definition of this instruction is, of this variable rather. That's the current instruction. So now that we've defined this thing, this instruction is now a candidate for deletion because the variable has been defined but not used yet, and there may be more uses later in the function. Notice I wrote def here, but of course what I meant was dest. So this is pseudocode that implements our first sort of local optimization that has to reason about the actual order of instructions. This one, you will find, has a similar problem to the previous one, which is that it sort of peels away one level of dead code, but it makes sense to keep on doing that iteratively until we have pruned away chains of dead code. So to make this work in a real system, we'll want to take this entire program and wrap it a big while loop that says like, while the basic block didn't change, and do this iteratively until convergence. But beyond that, we now have a more powerful dead code elimination pass that uses local analysis to complement the global analysis, the simple global analysis we saw in the previous pass. Pseudocode is all well and good, but now it's time to get to implementing. Please take the pseudocode you've written for these dead code elimination passes and code them up in, again, whatever language you like. you should implement both of the passes, and you should iterate them to convergence so that they are as powerful dead code elimination passes you can muster based on this framework. There's, of course, other ways to eliminate dead code you don't need to explore. Just take these two passes that we have designed so far and implement them in real code. I'm going to show you a pass that I have written that is available in open source, but you should absolutely not look at as part of the exercise of developing this algorithm yourself. And I'm going to show you how to run this on real code. In the notes for this lesson, there are links to various test programs that you can run your dead code elimination pass on. I'm now going to show you how I run my implementation of a dead code elimination pass on some of those examples. So those examples happen to be under examples in this test directory, and then there's this TDC stands for trivial dead code elimination because there's much fancier dead code elimination passes that could possibly exist. And then one of the programs I've showed you is just called simple.brill in here. So you will recognize this from the handwritten notes from before. And all I would like to do is optimize this. But first of all, I think it would be nice to start by just running this program. And the way you do that, of course, is with your old friend Brill to JSON that takes this text format that's easy to like write and look at and converts it to JSON. And then I can pipe that into the Brill interpreter. You're familiar with this. But one extra thing that I'll show you is that the Brill interpreter has an extra flag called -p, which is for profile, which will run the program like normal, but also print out some very, very simple profiling information, in particular, the total number of dynamic instructions executed. Here, 5. There are 5 instructions. They all ran exactly once. So that's 5 instruction executions. You can use this as kind of a very simple metric to see whether you are in fact optimizing programs by deleting instructions that actually would have been run otherwise. So the program in some abstract model of computer performance goes faster, whatever that means. So I'll show you what it looks like to run my pass. I have a program that's just called tdce.py. And if I run that and I pipe it back into Brill to text, then I can see that this program is transformed. And I have successfully eliminated one instruction from this program. If I wanted to, I could just use the word count utility wc-l. If I count the lines in the original program, well, there are 7 lines, and if I now pipe this all the way through this pipeline and I pipe that through wc-l, then I can see that I've eliminated 1 line of code from this, but that's not as useful as knowing the dynamic instruction count. So instead, it makes sense to pipe this into the Brill interpreter with the profiling flag. And there's 2 super important things here. One is that we get the correct answer. That is the same answer as the unoptimized program. If you did an optimization that didn't do that, it wouldn't be a very good optimization no matter how fast it makes the program run. But also, it's nice to know that the total number of dynamic instructions executed went from 5 to 4. Of course, beyond this, you probably want to run your optimization on more complicated examples. And fortunately, there is a little mini benchmark suite that comes with Brill that you extended last week as part of the first tasks for 6120. So for example, one of the benchmarks under here, there's a FizzBuzz benchmark. We can Brill to JSON that benchmark and then pipe it into the interpreter. And it needs an argument. So here we'll give it, for example, 5. And it runs some things, it prints some stuff, it tells us how many instructions it executed. It'd be nice to know if our optimization has any effect on this. So I'll run my implementation of this thing. I'll run in a more advanced mode just to see what happens. And I will pass it into the interpreter. And it tells us that we eliminated 4 whole dynamic instructions. Well, that's not a terribly large amount. But anyway, you can see that this optimized a somewhat more real-ish program than the tiny test examples that are just looking for correctness. Have fun. I encourage you to, for example, use Turnt to avoid typing out these very long command line invocations. And so you can have a nice pleasant workflow while you develop your first optimization that is hopefully the first in a long journey of very cool optimizations you will write during the course of 6120.